Hello everyone, welcome back to Computer Programming for Chemical Engineer course. And today I'm going to demonstrate how to solve root finding problem using Secant method. This is part of undergraduate program at Chemical Engineering UGM Indonesia. Okay, the learning outcome of today's exercise, after this exercise or after this course, students should be able to develop computer program for root finding problem. And in this case, we will use secant method, and the problem that we are going to solve is problem which is relevant for chemical engineering. Secondly, you are supposed to be able to design a program structure that combines for loop and root finding problem. In this exercise, as I said earlier, we will use secant method. The secant method is basically very similar to Newton-Raphson method, where the x new here is equal to x old or xi minus fx divided by the first derivative of fx. The value of the first derivative fx and x is approximated using numerical method. For instance, in this exercise, I am going to use small perturbation around xi. In this exercise, we are going to solve a problem related to transportation of fluid from tank 1 to tank 2. And this problem is adapted from the book of Modelan Matematis and Penyelesaian Numeris by Professor Wahyudi Sediawan and Agus Pras. So you can check on your textbook as well. In this exercise, we are going to transfer liquid fluid from tank 1 to tank 2 using pump and pipe. The narration of the problem is given here. A liquid is transferred from tank 1 to tank 2 with a pump via a pipe with diameter dp. And we already have the information about the equivalent length of the pipe as well as the fitting. And then the characteristic of centrifugal pump, it is given as a function of cubic equation and as a function of Q. Q is the flow rate, and as we all know that the flow rate is P over 4 multiplied by D squared times V. In order to get the velocity of the liquid, we can apply Bernoulli equation between point 1 and 2. Here is point 1 and here is the point 2. And hence, we obtain this equation Z2 minus Z1 plus FLE V squared divided by 2G dP minus HM. And this is the target function that should be zeroed. And we know that friction factor here, the F, is a function of Reynolds, and Reynolds number is rho V dP per mu. And you are asked to estimate the liquid velocity and flow rate in the pipe by using secant method. You're also supposed to plot the value of V for various value of dP, which is in this case is pipe diameter, and it ranges from 1 to 10 centimeter. And for your calculation data, rho, mu, g, z1, z2, and le is already given. In order to solve this exercise, the structure of the program can be described as follows. The first part here, it is main program, and here is the place where we provide data, calculation process, and we have for loop to access each dp span, and then plotting and preparing a table. The second part of this program is secant program, where it receives information about what is the V, and then what is the dp, and then this V dp is transferred to the third part of the program. This is to calculate the F. F is the output that should be zeroed, and then it will return F, and then the secant problem will give the root equation. And then the root will be stored in a vector, so we have a number of velocity for different value of pipe diameter. So this is the expected result from this exercise. Okay, now I would like to begin my exercise here. So we'll do it in Spyder. This is Spyder, and we begin with importing library. We can import here, import numpy as np, and then we also import plotting library matplotlib.py. SPLT. Okay, after we plot or after we import the library, we can prepare a place for data and then subroutine 1, this is for part number 3, and then subroutine 2, this is for secant program, and then the main program to call all the subroutine. And to speed up the writing process, I have copied all information here about the data. So this is the data that we can define from this problem. We have the tolerance that we can set to small number, and then x old, this is the initial guess of the velocity, and then the number of segment 19 in this case, and then the pipe diameter, it range from 1 to 10, and we divide it into nz segment, and rho, mu, z2, z1, equivalent length, leg, epsilon for small perturbation is already provided. Okay, so in this exercise, the first subroutine, as I said earlier, this is for program number 3. This is the f that should be zeroed. In this case, it is from Bernoulli equation. So we can type, this is how do we define subroutine, def, we call it my fun, and it receives information about velocity and pipe diameter, and it will return f. Okay, so when you have phi and dp, you can calculate f, and to speed up this exercise, I already write them in Notepad, so I can just copy. This is basically the same as you obtain from the problem. Oops, okay. All right. Oops. So basically, when you have phi and dp, you can calculate what we call as volumetric flow rate. That's pi over 4 multiplied by dp square multiplied by phi. And then you can also calculate the head pump, which is a function of q, and then the Reynolds, and then the friction factor, and finally this is the Bernoulli equation that should be zeroed. So when you have this subroutine, when you are done with that, we continue to make the second part of the program, that's secant program, and the input is phi and dp, which is in this case is phi gas. What is the phi gas to solve this problem? And to make this subroutine, we define what is we call it secant, and it receives input of phi gas and dp. Okay, and we can define what is the error here. Error is large number 1 in this case, for instance, and then we start making while loop, and this will continue until what we call as error lower than the tolerance. So while error is larger than tolerance, this will go continue. Okay, we start with f plus. Let's make a small perturbation to the forward directions. We call it my fun, and here is a phi, and we call it phi plus epsilon, and then that's dp. So that's the f plus. And then in addition, we also f minus. That's basically the backward step, phi minus epsilon dp. So you calculate what is the f plus and f minus, then you can estimate the first derivative. In this case is dfx. That's basically we estimate using center approach. That's f plus minus f minus f plus minus f minus divided by 2 multiplied by epsilon. Okay, when you have dfx, you can estimate what we have x nu. X nu, that's phi gas, and then the x old here is the same as phi gas. Okay, the x nu is x old minus fx But then the function at x we can estimate as fx. That's actually my fun x old comma dp. All right, fx divided by the fx. So then this will continue and continue to get the value of x new. Once you get x new, you need to calculate error. And okay, let's define residual as x old minus x new divided by x new. And the error here is equal to np dot absolute of this residual. So this is something that we want to minimize the error here. And once you have x new, you replace the x old with x new. So this is basically the main part of secant problem. And we have phi here. Okay, if I use x old here, so I need to write x old. So to make a general programming for any purpose, I just can type x old x new like this. And this will continue and continue until you get the root, and then that's the return, or call it x new. All right. Note that the indentation here, the return is in the outside of while loop. So if the while loop has finished, so we need to extract the x new value. All right. So now in the main program, in this part, we can test our value with, let's say, what is the velocity if v out, if we use x old here, the phi guess, x old, and then 4 centimeter as the pipe diameter, and then we print. This is just to make sure that our program works. Okay, so there is a problem with indentation. Oh, here. Oops. All right, it works now. So how to read this result? If you have x old, in this case x old is 200, and then if the pipe diameter is 4 centimeters, then you will obtain the liquid velocity as 227.67. And now the thing is, we would like to have the velocity for various value of pipe diameter. Hence, we need something called for loop, okay? For I in range from 0 to the length of dp span. Have we defined dp span earlier? So we have defined dp span is 1 up to 10, and we divide it into nz parts, okay? So for I in range 0 up to length of dp span, and we can check. Okay, I say dp now is actually dp span with index I, and then v out I secant x old, and then that's dp now, and this for loop will continue and continue. All right, so as you see here that Python require us to define what is undefined name v out, and usually v out, that's just empty zeros with zeros factor, I would say, and the size is the length of dp span. All right, so we can try now, see how it works. All right, we can print v out. Okay, v out equal to, and the format is 4.2 float, and then that's actually v out I. Okay, so we'll print various value of v out. Maybe it's better if we clear the screen and then see how it works. Okay, now we can see the value of v out for different value of dp. To make it better, maybe I can also print the dp equal to 4.2 float number, and then that's dp now, and then v out I. Alright, let's check again. Now you can see here the value of, if you use dp equal to 1, the v out is 199 and so on. If 4 is 227, and if the dp is 10, you will get the v out 54.6. Now you want to make this vertical line as a straight line. You can provide more space there for the second part. Oops, we need to provide more space there. Maybe 8 is enough. Maybe it's too many. Okay, now we already have table showing the pipe diameters and their the liquid velocity, and we can also print the value of fx to make sure that the value of fx is very close to 0. I mean this one. So as you see here, if you want to run this file, you need to supply what's the v and dp, and you call it my fun. So you can check y out I, that's equal to my fun v out I as sv, and then as dp you can call dp now, right? And then again, Python will suggest us to make pre-allocation. You just can copy this one, v out y out. So y out is here, and we can check the value of fx equal to, so this is percent and then 4.2, and the format is scientific or E, and then you can type y out there, and the value of x should be very close to 0. Oops. Y out I. Alright, check again. Oops. It's better to have line there. And provide more space. Yeah. Maybe more space. Yes. Now you can see here that the fx value is very close to 0. 10 to the power of minus 12, minus 13. That looks very good. Okay, now we can make this table a little bit better by printing the header. We can print, for instance, this one. We can multiply by 35. Let's see how it looks like. And then you can print the header as dp, and then v out or velocity, and then fx. Usually it's not gonna be a straight table. You'll see how it looks like. As you see here, you need to move the velocity a little bit to the right, so you can provide more space there. DP is okay, but then the velocity needs a little bit more tabs. Velocity is good, and now fx, maybe 2 is enough. Oh, one more time, you can put it after fx. Okay, good. So this is the table, and as you see here, there is still some missing space. We can put 40, and then we can have more lines under this one. Alright, so we are done now with making table of our computation. Now we would like to make a plot. It's very simple actually. You can put plt dot plot. The x-axis is dp span, and then the y-axis is v out. And you can type blue, and then it is circle, oops, O, and then the marker size I usually put 14, and then plt grid, sorry, plt.grid, and then usually we type plt.y label. Y label is basically velocity, that's in centimeter per second. And then the y-axis plt.x label, and that's pipe diameter in centimeter. See how it looks like? Yeah, so this is the final results. It shows the liquid velocity for various value of pipe diameter, and this is the table. You can see here, you can make it a little bit wider there. So that's basically the end of this exercise. Before I close this exercise, I can show you again. The first one, you have to import the library and you provide all the data that you have here, and then the subroutine one for function of Bernoulli equation, and then subroutine number 2, you can provide the secant program, and this is the main program, and then the place for you to define or to make a plot. So this is the plot, how it looks like. So thank you for watching, hope you find it useful. Thank you.